Welcome back, everybody. Time to talk about the RF ground. I put this off for quite a while because, frankly, it is a big job. Anytime you talk about RF theories, things get complicated. The RF ground is just as complicated as everything else in radio. However, it is my goal to explain this simply to those with no technical background, or those that are just getting started in radio, or those that haven't thought deeply about some of these topics. Now, if you haven't, I suggest you look at 602 and 603 as a minimum, but if you don't worry. I'm going to review those in a minute. This is going to be an introductory lesson in RF ground. The next two videos, maybe three videos, I'm not 100% sure yet, I'm going to talk about the RF ground. When does it help? When does it not help? When does it cause worse performance than if you didn't have it at all? When does it cure noise? And when does the RF ground cause noise? Yes, all these are possible. All right, let's do a quick overview of grounding in general. I want to do this because I want to set in your mind what grounding is really all about. Why do we ground for lightning? This is a pretty simple one to explain. Lightning forms between a cloud and the ground, so it makes sense that if we can attach ourselves to either the cloud or the ground, maybe we can get out of the current path. Here's our ham station. Now, if you would, notice that I've done my best. I've grounded my tower. We've got a ground at the circuit breaker panel. We've got a ground at the pole. I should be ready for lightning. Unfortunately, this is not a good grounding situation. Mean old Mr. Cloud comes over with probably a negative charge. I'm not going to debate charging whether the cloud is positive or negative. I'm not going to debate which direction the electron flow happens because we don't care. All we know is current flow is happening and we got to do something about it. In any event, what we want to happen is all that current to travel between cloud and ground through the tower ground because we're assuming that's what's getting hit. If it was hitting the power pole, we'd want it all to go down into the ground at the power pole. Unfortunately, current divides among all paths in inverse proportion to the resistance of each path. So we end up with something that might look like this, which is not good. Our radio just got blown up, even though we grounded everything like everyone told us we were supposed to. The way to fix this is to take the radio out of the path. So we do this. We bond all our grounds together. Then we put in this clever bulkhead panel here, and we bring all of our wires through it to our radio. Guess what happens now? We still get the same current. I gotta get my little cursor going here. The current comes in. Most of it goes to ground through this network here. A little bit of it is going to follow the third wire. Hopefully not very much. But notice, no matter what happens, there's no path through the radio because it's all tied up in this panel. The radio might elevate to 1,000 volts above ground, but it goes up smoothly and comes right back down. You might get a little bit of a shock if you're touching the radio when the lightning hits if you're well grounded, but you probably won't. Anyway, the point of all of this is lightning is not trying to strike your equipment or you. Lightning flows between the cloud and the ground. What we're doing when we ground is we're really bonding to Earth, so we're part of the Earth, and we're not a victim of the lightning. So it makes sense to ground for lightning, obviously. We ground because the Earth, that is the ground, is where the current is going. So in this context, ground is a connection or reference to the conducting Earth. Why do we ground the power system? Well, because of lightning, first of all, so the answer is the same as the lightning ground. Except there's a little more to it. Forget lightning for a minute and just think about what went on several generations ago. We had outlets that had two evenly sized prongs. One was hot and one was ground. We didn't know which one necessarily. appliances didn't care. This is the plug on my 55-year-old HW16. This is a schematic of the input to the HW16. You might notice neither side is tied to ground in the cabinet. But what do you suppose is going to happen if this capacitor shorts? Now you've got the hot lead touching the cabinet. If I touch the cabinet and I'm also in contact with ground or a grounded object, I become part of the circuit and I'm electrocuted. One of the things they did to try to get around this is they invented the polarized outlet. Now one blade is wider, so this is tied to ground. Except if you don't ground the cabinet, which Heathkit did not do in this case, and this still touches the cabinet, this is still a hot cabinet, and if I touch it, I get electrocuted. So this kind of worked. I mean, it kind of helped. If they would have tied this to ground, we would have been okay. Heathkit decided not to do that because sometimes tying one side of the power line to the cabinet can cause RF interference. That's a topic for another video. Anyway, what we ended up doing is we came up with the 3-wire plug, which does a lot of things. First of all, the cabinet is always at ground. So if this hot lead comes in here and touches the cabinet, a lot of current flows through the ground back to here, and this fuse blows. Also, notice that because the cabinet's tied to ground, the cabinet, if this 3rd wire is intact, the cabinet can't go above ground potential and it's not a danger to us. So the point of all of this is that we ground by tying the incoming neutral wire to the earth ground. And doing so, we establish a way of keeping us safe. In this case, ground refers to earthing. That is, we connect the neutral or return path to earth ground. In this context, ground is a connection or reference to the conducting earth. So again, we've figured out now why we do a safety ground and a lightning ground to the earth. In these contexts, both of them, ground is a connection or reference to the conducting earth. What about ground in vehicles? There's no connection to the conducting earth in a vehicle. Here, ground refers to a shared voltage reference between circuits in the vehicle. Now, when it comes to an RF ground in a vehicle, that's another video, and I'll get to it. But apart from the vehicle RF ground, what is the RF ground? How do we define RF ground? We could pick up a university physics book, which is a favorite, or was a favorite, a generation ago in RF and electrical engineering classes. And the very first thing you're going to notice is, well, I got to control my cursor here, sorry. There's no real talk about ground as in RF ground. He talks about resistance and reflections, but there's no RF ground. He does talk about RF shielding. Well, all right, maybe the RF ground is a myth if a university textbook doesn't talk about it. What about the American Radio Relay League? Certainly they must talk about it. They don't talk about an RF ground. Now they do talk about radio frequency interference and grounding and bonding for radio frequency interference. Maybe that's a clue. But no, an electrical ground is not a huge sink that somehow swallows noise and unwanted signals. Ground is a circuit concept, whether the circuit is small, like a radio receiver, or large, like the path between a transmitter and an AM/FM receiver. Ground refers to a shared reference voltage between circuits. Now they threw that thing in there about the path between the transmitter and the receiver. That's a little bit confusing because that is a path. But don't get the idea that they're saying your radio signal goes from your transmitter to the other guy's receiver and then it somehow comes back to you through the ground. That's not what they're saying. So does all this mean that the RF ground is a myth? Some say it is, but I kind of think that's throwing the baby out with the bathwater. Mr. Maxwell agrees. If you pick up Reflections, Reflections 2, or Reflections 3, I am telling you, you are buying the best book on SWR, transmission line theory, wave theory. This is the most understandable RF book I have ever bought and read, by far. And again, he doesn't really talk about an RF ground that much, but I'm going to come back to him in the second video. So no, the RF ground is not a myth. Now, before I move on, there's one thing I've got to mention. RF ground should not be confused with the concept of the ground plane antenna. I'm going to do a separate video on just the ground plane antenna, hopefully by the end of the year of 2025. Just keep in mind, not all vertical antennas are a ground plane antenna. And again, I will come back to that later. So why the RF ground? Why are we hearing so much about it, and why is there so much concern for it? Can an RF ground make our antenna work better? Can it fight noise issues? Can it keep RF out of our shack? Well, the last two questions, for the most part, I'm going to save for video number 2. In this video, I just want to talk about whether or not an RF ground can make our antenna work better. See, the only way an RF ground could improve an antenna's performance would be in the management, that is to say the improvement, of current flow in the antenna. Remember, radiation is produced by your antenna using current flow, charge distribution, and charge acceleration. Now that's a lot of physics. You don't have to remember all that. Just remember one thing. If you can increase and improve current flow in your antenna is going to work better. Now, how would an RF ground help? If an RF ground can do anything, it's going to do it by improving current flow at the feed point, because we can't directly work on current throughout the antenna, but we have a lot of control over the feed point. And if you've been around ham radio for very long, you've already heard about common mode current and reflected waves and all that kind of stuff. So this should give you a clue that an RF ground certainly does or can play a good role here. Let's talk about making the antenna work better through improved antenna currents. I want to talk about 4 separate kinds of antennas. The dipole with balanced feed, that's like ladder line or twin lead. The dipole with a coax feeder. The ground plane, really all vertical antennas. And then end-fed wires, specifically the end-fed half wave. All of this applies to the so-called long wire and the random wire. Let's start with a dipole with balanced feed. Well, here we go. Now, I'm not showing you the radio or the watt meter or the SWR bridge, just the tuner, the feed line, and the antenna. This is an antenna being fed with what certainly looks to me like 450 ohm ladder line, but whatever it is, it's balanced twin lead. Now, just for the sake of making things easy, the line we're going to say is exactly a half wave long. This is not a big deal, but it kind of helps. What is a big deal is for my math and diagrams to work, the antenna must be a half wave dipole. All right, so we agree. Oh, look at the tuner. You might notice, like my tuner is a link coupled tuner. There's just 2 big coils and some capacitors in there, and one of the coils feeds the line and switches each pole from positive to negative as the sine wave progresses. Now, some tuners have a toroid core feeding the line, but electrically it would look the same. All right, so what happens when one side goes positive, the other side goes negative, is you get current flow. Now, don't let it bother you that we've got current flowing in antenna wires that are not a complete circuit. Like if that was a loop antenna, it would make sense that current could flow. How can current flow when there's no complete circuit? That's the subject of yet another video I want to do. But for right now, just keep in mind that At RF frequencies, due to charge acceleration, the only thing I need to make current flow into here and out here is enough conducting surface to make the current happen. You'll notice there's no current at the end, but there's a lot of current here. There's a lot of current here, but there's no current at the end. The idea here is if we reverse the polarity of the sine wave fast enough, we can get those charges to turn around before they kind of realize they have nowhere to go. That's the best way I can explain it right now. I'll explain it better in a later video. All right, so when the polarity changes, of course, everything changes back. I want you to notice something super important. Notice that there's a negative voltage here that gets higher at the end, and there's a negative current that gets lower at the end. Here, there's a positive voltage that gets higher at the end. Here, there's a positive current that gets less at the end. Notice how balanced everything is. So what we have here is, all right, we have a great, oh, my marker is not working. Why is my marker not working? There we go. We have a great voltage gradient across the antenna. This means there's an electric field generated across the antenna. This electric field is horizontally polarized. That means the antenna, we say, is horizontally polarized. It is generating magnetic fields from the current in the antenna. The magnetic fields are vertically polarized. The electric field is horizontally polarized. So therefore, we have a horizontally polarized antenna. What's really important to note is how balanced all the currents and voltages are. Everything is symmetrical. This leads us to a conclusion. Nothing here is referenced to ground. The positive and negative are in relation to each other. If you tried to measure the voltage from either side of the antenna to ground, you'd get an erroneous reading because we're not referenced to ground in any way. And we don't need a ground. In fact, no RF ground will improve current flow or radiation from this antenna. Does this prove that an RF ground can never help? No, it just proves it doesn't help with this antenna. And this is not to say that a safety ground or lightning ground is not important. That's a different topic. What isn't a different topic, and I'm going to venture into the noise environment just for a minute, is this antenna is hanging in the sky, and as you can see, there's no path to ground. If we develop a static charge in the antenna, it has nowhere to go, which is kind of not a good thing. So if we were using a 2060 series tuner and most MFJ tuners, we'll find the center of the coil is set to cabinet ground. This is not an RF ground, and you don't need an RF ground. What you really want is just to ground back on the third wire or a reasonable ground, because taking that static charge off is very easy because the static charge has a very slow rise time. So you can coil up your ground wire, you can run it 300 feet, and there's not a lot of consequence to that. I wouldn't do that, but you could get away with it. So the static ground, which I haven't talked about a lot, isn't that hard to get. All right, so an RF ground does not play a significant role in feeding this antenna. What about the coax-fed dipole? We've all heard about what a mess those are and how you need a balun and all that stuff. Let's look at that. Here's our basic dipole, no balun. Here's what's going on inside. Balanced, perfectly balanced currents. Current comes in on the center conductor, goes out on the inside of the shield. When the polarity reverses, you get this. Now you're probably thinking to yourself, wait a minute, how can the shield be positive? Well, it can't be positive. In fact, let's take a good close look at this, because this is where we get into a lot of trouble. Notice this is the antenna connector. This green is the cabinet of your radio. It's tied to ground through the third wire, or your station ground or whatever. Okay. Now, the transmitter generates this sine wave RF signal. The center conductor is swinging positive to negative The shield is staying at ground. So when we say the shield is positive, what we mean is the center conductor just went negative. So the shield is positive with respect to the center conductor, but it actually never changed voltage. That's the problem. For this antenna current to form, this junction here has to go negative. Technically, it can't, because the coax shield is supposed to be grounded and at ground potential. Now, at certain wavelengths of coax, that kind of varies a little bit. The way to fix this is we want this shield to stay at ground, this to swing high and low, and these two to swing together in opposite polarity like the ladder line fed dipole. The way we do that is we introduce the one-to-one balun transformer. That way, like all transformers, each side can do its own thing and energy is transferred, and transferred well. So this is the right way to do it, and it solves that imbalance problem because now the shield connected half of the antenna can swing in voltage without any problem because it's no longer physically connected to the shield going back to the station. Now, you're going to get my opinion. This is my opinion, it is not fact. I think the balun is a waste of time. In 50 years, I've never used one. My antennas, my dipoles work just fine. Am I feeding them properly? No. Is my antenna pattern screwed up? Yes. Am I getting a little extra RF in the shack? Well, I haven't noticed any at 600 watts out, but I'm sure I am. I just don't care. But I'm telling you, the right way to do it is to use the balun and don't do it my way. But I am also saying you don't necessarily have to put the balun in there. You can let things go haywire if you want to, which is what I do. Not very professional, but I'm a ham operator. All right, so we've decided an RF ground does not appear to play a significant role in feeding this antenna or correcting its issues, but a properly designed balun will help in correcting those issues, and it will improve feed point and antenna current. Notice I said an RF ground does not appear to play a role. I'm going to come back to this in the second video and expand on it. Let's talk about the verticals. This will be a quick talk. You're familiar with this. Again, we're going to impose this current. We're going to try to keep the coax braid at ground. We're going to get current flowing like we normally do. The other half of the cycle, the current's going to reverse. Why can't we just do away with those stupid radials and put a ground in? Well, you'll notice what I did. I made the arrows smaller. The reason? At ham frequencies, especially, ground conductivity at RF isn't that good. You can't just flow current in and out of the ground that well. So yeah, this kind of works, and in some areas it works rather well because the ground conductivity is really good. I'm going to come back to that in another video. But generally speaking, most of us can't get away with this. Now, ground conductivity down at the AM broadcast band is not sufficient to negate the requirement for 120 radials at an AM broadcast station. Some people think that AM stations are grounded for RF. They're really not. They're grounded for lightning. If an AM station didn't need 120 radials, it wouldn't have 120 radials. Although, like I said, depending on the ground conductivity in the area the station is, it may or may not get a little better ground current going. To the best of my knowledge, and one of my friends is a broadcast engineer, the FCC is still requiring approximately 120 radials to make the antenna work properly. But again, this relates to the ground plane thing, and I'm going to come back to this in the second or maybe third video. I've not decided how I want to write the second video yet. So an RF ground could help support feed line and antenna current if we could get enough ground conductivity, which again, especially above about 3 megahertz, that's simply not going to happen. All right, End-fed wires. This is the fun one. This is the one everyone wants to talk about. And frankly, this one applies more than anything else to the concept of the RF ground. Here we go back to an RF transformer. And as you know, we're going to apply power to the left side from our transmitter. At times, the bottom of the secondary will turn positive and we'll get current flow. When the next half of the cycle comes along, the top half is positive and the current goes the other way. Very simple. But at your end-fed half wave, it's wound like this. Let me blow it up. At times, the top will be negative. Other times, it'll be positive. How can we have current flow at the top if we don't have current flow at the bottom? Because there's nowhere for it to go, right? Well, there is somewhere for it to go. It goes like that. That's a problem. Here we go. We've got our line. Just to be clear, this is an actual end-fed, I guess you call it a unen or ballon. And let me get my pointer out here. Here we go. All right, here's our ground lug right here. Here's the shell of our coax connector right here. They're tied together. The bottom of both coils are tied to both. All right. The center pin is right here. It just goes through this coil. All right. So it goes up through here, goes through a couple coils, comes back. The other coil comes off the antenna, goes all the way through this, and then down to the common. All right. See right through here. Okay. So I'm just showing you my schematic is accurate, at least for Kelly Smith's ballon, because he's the one that sent me a picture of his. All right, so we're going to excite the thing. We have no ground. We have nothing. Let's say the top of the coil turns positive, so current starts to flow. So naturally, it flows out of the coil down the coax, which of course we don't want. This is putting RF in our shack, possibly causing some other problems. So we put some ferrite beads in there to stop that current. The result is we reduce all the current flow. We've got the RF out of our shack by reducing the performance of the antenna. That's not what we wanted to do. We could put a ground in and source and sink current into the ground, but as I've already said, probably don't have the ground conductivity to do that. Why don't we do this? Let's put up a quarter wavelength long piece of wire. Now you can use other lengths, but it's best to use a quarter wave or a 3/4 wave or a 5/4 wave. In other words, a multiple of a quarter wave, an odd multiple. I talk about this in my 400 series, why it has to be an odd multiple of a quarter wave. This will work well. Now, this counterpoise wire we just laid out does try to radiate a little bit, but the point is we're giving the secondary coil somewhere to suck and deposit electrons through the sine wave cycle. It doesn't matter that our counterpoise wire is a quarter wave long and our big wire is like 2 wavelengths long. That's not a problem. We just need at least a quarter wavelength piece of wire to sink and source electrons when the current flows. Now, it's a good idea to have a radial a quarter wave long for each band. Although if you had a 33-foot radial, that'll work on 40 meters, but it will also be 3/4 of a wave long on 15. So maybe put 2 out, one for 40 and 15 and one for 20 meters. If you want to run 10 meters, put a third one out that's an 8.5 feet long. So an RF ground could help support feed line and antenna current in the end-fed wire if we only could come up with enough ground conductivity. Now, that's it for today, or for this one. It's been long enough. It's 29 minutes. In the next 2 videos, I'm going to go back to ground plane and dipole antennas. I'll talk about noise. I'll talk about RF in the shack. And I'll talk about what would happen if we did put a ground on the end of the end-fed half-wave wire antenna. In other words, what if we took that ground lug that we have our counterpoise on, or our radial, and we also tied it to ground? What would happen? Anyway, I'll talk about this and noise and all that stuff in the next video. Just for just a moment here, I thought I'd throw these yellow ones up. This talks about some of the things we just talked about. The videos up at the top of the page. And if I can get my pointer to work here. All right. So these talk about what we were just talking about to some extent. If you watch 603, it talks about rise time and talks about grounding for EMPs, RF, lightning, all that stuff. I tried to keep the math simple, but I put enough in there so you understand why we're concerned about rise time and what rise time is. It's not that hard to understand. Now, one thing, WHJI, Tom Roush, he is the engineer behind a lot of the MFJ and Ameritron RF products. His website is always a wonderful place to go read and look at stuff. I recommend, if you don't already have a Radio Amateur's Handbook and a Radio Amateur's Antenna book, go on eBay and find used older books cheap and buy them. You don't have to have this year's model. If you can come up with any edition of Walter Maxwell's Reflections, any of the three, I encourage you to grab one of those too. Those will cost you a little more money. Now, if you're happy and good and comfortable with single variable calculus and things like that, go to YouTube and search Walter Lewin 8.02, but be ready because he can't do anything without calculus. Antennas by John Krause won't tell you how to build an antenna, but it gives you the theoretical stuff of how antennas work. It's kind of deep. There's a fair amount of math in it. His book Electromagnetics is kind of like Walter Lewin's YouTube stuff. If you're not good with calculus, it's very hard to get anything out of his books. But anyway, I thought I'd throw these up here as references and as additional material. Anyway, next time I will talk about all the things I just promised to. Watch out for me to post 605 and maybe 606 by early December 2025. Thanks for watching, and I'll see you next time.